All right, hello everyone. Thank you for coming. We're very excited today to welcome Thomas Harvey for today's IAIFI Colloquium. Thomas very recently joined us as an IAIFI fellow after completing his graduate studies at Oxford. And Thomas studies string theory and its connection to particle physics and cosmology. He's also been at the forefront of applying various machine learning techniques to this intersection. And today he's going to tell us about how we too might navigate the string landscape with machine learning techniques. So whenever you're ready.
Okay, yeah. Thank you for the lovely introduction. I'm just going to begin by saying that, okay, so there are a few people in the room who are more from a Hecke theory background or from actually specifically a string theory background. I've tried to put this more of a colloquium style to make it as accessible to the broad audience as possible. But feel free to, interject with more technical questions or whatever, or ask me or actually get involved in some of this work afterwards. But yes, I'm going to try to make it as understandable for the broad audience as possible. So yeah, this is really kind of by being more overview. Don't get too scared of the number of papers on the bottom. I've kind of taken just a few bits from each of them to give the kind of broad idea of what's of the kind of things that I've been thinking about and been working on. I think collaboration with a number of people. I guess the person here that people are most likely familiar with is Bert Tucker, who's based in the United States. He's at University of Pennsylvania. But aside from that as well, a few other people. So Steve Abel, who's at University of Durham in the UK, as well as people from my old Oxford group, so Andrew Constantine, my old supervisor, Andre Lucas, and of course Kits, who is visiting for the next few weeks. So feel free to also ask him about, I don't know, what do you want to be asked about for the next few weeks? Anything interesting? There you go. Right. Okay. So yeah, just to get started. Because it's a broad audience, and unfortunately because of the nature of some of the opinions people sometimes have of string theory, I feel the need to give a defense of string theory at the start of it, and then I'll then go into some more specifics. So if you just literally Google why string theory, you might find this picture. It is, and it makes the rounds on Twitter every few years, which is from a popular science book. And it says, well, there's a chapter 7 of this book, it just says, what is the direct experimental evidence for string theory? And the whole chapter is just one sentence, which of course says, there is no direct experimental evidence for string theory. But, I can't disagree with it. It's 100% true. But to give you a little bit more context for this, and why I think this is definitely taken out of context whenever this makes the rounds on the internet, is let's just go look up who wrote this book. And it's written by someone called Joe Cosman. And if you just go look at some of his recent publications, you can notice string theory in the first half of the universe. On the dark, out of the dark, string theory in the universe, string theory of the universe, an open full information of high dimensional objects. These are all definitely string theory topics. So what's going on here? Because it doesn't seem like it was written by the same person from what you're seeing on the left-hand side. And the reason for it is that the whole point of this book, it's literally called Why String Theory. And it's really saying that despite the fact this is the case, why is it so many people are interested in string theory, and why is it an interesting topic? To study both from a kind of mathematical physics point of view, as well as a theoretical physics point of view. So just to give you some of the reasons to why maybe you should be interested in it, so just to begin kind of a more formal point, that string theory exhibits certain dualities and also led to the discovery of holography, which has allowed for calculations in kind of previously inaccessible areas of theory space. So in particular, strongly coupled theories, it gives you some kind of handle on particular strongly coupled theories. At the same time as well, it's really kind of developed our understanding of the quantum nature of black holes. So there's this famous calculation by Hawking, kind of semi-classical calculation where the entropy of a black hole, but it gives no understanding of what microstates lead to this entropy. But in string theory, you can actually identify those microstates in some cases and count them, and you realize it's an agreement with Hawking. Along with that as well, string theory has led to several interesting connections in mathematics. In particular, something called mirror symmetry, which was unknown to mathematicians studying particular types of manifolds at the time. This really came out of the study of string theory. But from a physics point of view, there's still reasons you might be interested in it. In particular, that string theory quite literally it's not the, well, yeah, it is a theory of quantum gravity. Sure, there's the debate, is it the right theory of quantum gravity? But it's definitely a theory of quantum gravity. And I think there's arguments to be made that it's really the only one we really have a kind of considerable handle of at the present time. But not only that, but it also contains gauge theories and chirality, which are really the basis of all particle physics we have today. So it really is a contender for a theory to describe our world. Okay, so given that those are some reasons why I think you should at least be interested in string theory, maybe I should try and tell you what string theory is. And in its present form, that is quite hard to answer. And the reason for it is that you might look at string theory in different points of view and what looks like the fundamental degrees of freedom change. Okay. But something that's very generic to it is that in all of these kind of regions, that particles, what you would expect to be particles, are replaced with different extended objects known as branes. Okay. Now, what these branes are depends a little bit on which where you are in this kind of space of string theory. But at least in the 5 best understood areas of it, these ones we're running outside here, the lightest and the lightest of these branes are one-dimensional objects called strings. Okay, but in other limits, for example, this thing down here, 11 dimensional supergravity, it actually appears that the natural degrees of freedom are even bigger objects, these 2-dimensional extended objects instead. But really, one key point here is that in all these cases, there are some higher dimensions. Okay, so in these 5 here, there is 10 space-time dimensions rather than the 4 we see. And in the bottom case one here, the 11 dimensional supergravity, I think from the name you can probably guess it has 11 space-time dimensions. So that's really kind of when you see string theory, when you first see string theory, this is clearly the first kind of problem that is going to be found to be. So what am I going to do with these extra dimensions I see here? Secondly, as is the case with basically every physics theory I know of, you need to specify some kind of initial conditions. Okay, so yeah, I don't know any theory where that's not the case, and string theory is exactly the same. But in this case, the initial conditions present themselves as I have to specify some 10-dimensional geometry, at which point string theory, the dynamics of string theory, will tell me what happens after that. Okay, so we can try and address both these problems at the same time. So what I'm going to do is I'm going to take from my initial ansatz, I'm going to say that my 10-dimensional spacetime is a 4-dimensional maximum dimensional space, the Yukawa space, multiplied by some compact 6-dimensional space. Okay. So if I now consider what my theory looks like as a 10D theory, given this ansatz, I can integrate out the extra dimensions and be left with an effective 4-dimensional theory, where the corrections to this 4-dimensional theory will vanish in the limit that the volume of that compact space becomes small. Okay, so that's all well and good, and it turns out that different choices then of this 6-dimensional space, as well as what your other fields that exist in 10 dimensions are doing over this compact space, will lead to a different effective theory in 4D. Okay, so it's kind of this task of a map from geometry to 4D to 4D rhythms. And kind of the general rule of thumb is that kind of at least quasi-topological data. I'm not going to go into what I really mean by quasi-topological, but yeah, topological data, so kind of discrete data of a compactification, gives you discrete data about a known theory. Okay, so it'll tell you, for example, how many families of quarks and leptons you have, or something like this. Or it might tell you something else discrete. So what gauge group do you have in the low energy theory? However, if you actually want to then try and get a handle of more kind of refined parts of the low energy theory, what you need to start doing is really looking at geometry as well. Okay, and I'm going to be addressing both parts of this in this talk, in particular how machine learning tools have been able to address both sides of that. Okay, and just kind of for a caveat here, as with any calculation, having some form of symmetry really assists you in the calculations. I mean, at the end of the day, what we're really trying to do here is we're trying to solve 6-dimensional or 6 or 10-dimensional Einstein field equations. I'm sure most people here have probably taken GR class at some point, and in a typical GR class, you're going to have to impose some kind of symmetry to solve the equations I mentioned, whether that be spherical symmetry or similar. And exactly the same is going to take place here, except in this case, rather than spherical symmetry, we're going to be making use of supersymmetry. Now, I'm going to say this is not to say that the effective theories that come out of this will, in the end, have low energy supersymmetry. Okay, there might be phenomenological reasons to why you find that appealing, but this is kind of the background which we'll then perturb away from. Okay, I'm not really going to go into the details of how you perturb away from it. Everything we're doing is going to exist at the compactification scale. But in principle, yeah, there's a difference between having my background being supersymmetric and actually perturbing away from that after the fact. From the geometry point of view, I'm just going to introduce this now because I'm going to end up saying it many times. This 6-dimensional space is something called a Calabi-Yau level. Also a Calabi-Yau threefold. This language might seem a little bit weird for why it's a threefold, but the reason for it is that this is a 6-dimensional space, but these Calabi-Yau manifolds are complex manifolds, so it's really complex. Okay. So that's the kind of overview of what string theory is and the kind of the starting point of what we're going to do. So let's say we wanted to try and get some approach to trying to engineer something that looked at least a little bit like us from string theory. What would be the kind of general structure you want to do? So, okay, well, you want to make sure you get the particle spectrum. And once you've got the correct particle spectrum, you need to make sure you do two other things as well. In particular, you want to make sure that you get the correct Yukawa couplings so that you actually have the measured masses and mixings for the particles you have in the gliders. But also, you have to do one other thing, which I'm going to address now, just in words, but I won't talk about it at this point. You do really want to do this thing called stabilized modular. So what does this mean? So, as I said, I'm specifying some initial conditions for my string theory. Okay. Now, and then dynamics will, okay. Yeah, I'm specifying some initial conditions for my string theory, and then string theory tells me the dynamics that then happens to this afterwards. And there's a general problem that you have whenever you do a string theory application, is that even if I set up my nice standard model by having some particular configuration, I let go of it, and naturally what happens is my small dimensions want to become large again. Okay. And so this problem of moduli stabilization is essentially trying to keep those extra dimensions small. Okay, I'm not really going to be talking about it too much detail today, but in principle, this is a problem for any of the stuff I'm talking about, and there are people who work on that as well. Okay, so moving away from that, what am I going to do then with my string theory application? So I have to specify one of my string theories. In particular, I'm going to take what's called the E8 cross E8 heterotic string theory. And not only does this have 10-dimensional gravity, but it has other stuff as well. In particular, might be in the name, it has some gauge fields, so the gauge group is E8 cross E8. Okay. And not only do I need to specify the Clavier manifolds that the geometry is going to be, but I have to say what is this gauge field going to do over the extra 6 dimensions. Okay. And this is encoded in what's called a vector bundle, which has to satisfy some topological conditions as well. But this vector bundle you can just kind of think of as being a description for how topologically non-trivial my field is winding over the complex space. That's kind of an intuitive picture that you should try and think of. Okay. So not only then do I have to specify this, I also have to say in particular, I have this huge E8 by E8. How much of that is going to actually take effect over the complex dimensions? So I have to try and split this up. Some of it will be I have to put on some part of it, on a vev, essentially a non-trivial vev, over the Clavier manifold. And then the commington of that in E8 will be the gauge group I see in the dimensions. So it turns out the bundles I'm able to kind of construct here are SU5, SU4, and SU3 bundles. And you look at the commingtons of that within a single E8, and ignore the second E8, what I'm doing. And what we find is the commingtons are SU5, SO10, and E6, which maybe the particle physicist amongst you might recognize that these are the kind of the gut groups that are studied by the XM models and such. Now, the way I'm going to eventually break this to standard model is not by having some kind of gut fix. Instead, I'm going to use something called discrete Wilson maps. Now, I'm not going to go too much into details of this, but the point is that it's a way of breaking a gauge group down that involves the extra dimensions. It doesn't need me to introduce any more groups. Okay. So you're going to click on. There we go. Okay. So, like I said before, I need to specify a Clavier manifold. So vector bundle saying what my gauge fields are doing, and then the appropriate Wilson map. Given this geometric data, which is discrete data, it's normally specified by large number of integers, I can go away and I can calculate the low energy massive spectrum that would come out of this string application. Okay, in particular from a type of topological property known as Cosman. Okay, and what's quite nice about this is that even though really what I want to do is solve the equations of motion of string theory, there are these powerful theorems by Yao, or Yao's theorem, Yao, Lao Yao, and Donaldson Yao, which tell me that given some specific set of topological conditions on this, there exists a unique solution for the metric in the gauge field. So I can guarantee that without even solving the equations explicitly, I have an existence proof that there is a solution. And so to some level, really, most of what people have been doing in string theory for the last 40 years in string applications has entirely lived on this side for that exact reason. They never have to go away and calculate the metric in the gauge connections. Okay? Because if they're interested in, say, the mass spectrum, they don't need to actually go and calculate this. But as I said before, let's say I wanted to go further. I want to calculate some continuous parameters. Then what I actually really have to do is I do have to go and solve for the metric in the gauge connection over these complex spaces. Okay. And so again, really the first part of my talk is going to talk about this side of the graph, and then using methods of machine learning to search the space for potentially interesting topologies. The second part is going to be talking about using machine learning methods to solve eigendimensional partial differential equations to calculate these more refined properties of the energy theories. Okay. So, given all this string theory, now I can turn to why is machine learning necessarily, or why does it look like it should be a good tool for, why should machine learning be a good tool for string theory? And the first of these reasons is that string theory really does have big data. Okay. Now, I'm not going to go through what all these numbers mean exactly, except for the fact that, as you can see, these are giant numbers. Okay? And they're all numbers that are related to different properties of doing a string magnification. So you have 10 to the 400, 10 to the 500, 10 to the 200, 272,000. These are all giant numbers. And not only then has it got big data, but this data is also clean. It's not like some experimental data where you have to worry about experimental noise or anything like this. This is pure mathematics. And normally also comes from, it's normally integer data as well. But really, this is huge amounts of data that is entirely clean, you can generate in a computer. Okay. The second point then is that string theory has an inverse problem. Okay, so if I just specify on the spectrum for now, the particle spectrum I have in my low energy theory, then to work out the particular particle spectrum from the topological data, this involves an incredibly complicated math, in particular using a lot of tools that have been developed over the last 40 odd years in computational algebraic geometry. But the inverse problem is really not obvious. So if you say, I want to go over a particular 4D theory, say the Standard Model, or say you're interested in some other theory for purely mathematical physics reasons, working out exactly what geometric data would lead to it is really not easy. Okay, and so as a result of this, kind of both from the large numbers and also the fact this math is incredibly complicated, working out those few constructions which might lead to something of phenomenological interest is very, very difficult. Okay, so just kind of summarize those 2 points, and then a third point as well I mentioned about why machine learning and string theory. The first one is that you have these large data sets, and people often talk about conjecture generation, which is that it's mathematical data. Maybe there are patterns in this data that people haven't noticed before, or similarities in different things, that maybe leads to developments in pure mathematics, or string applications related to that. Secondly, as well, we have this inverse problem, and these problems of discrete optimization. And so in particular, tools like reinforcement learning and genetic algorithms have proven to be very useful tool in this area. And lastly, as I said before, we have to solve partial differential equations. In particular, we have to solve partial differential equations in very high dimensions. And it's proven to be that machine learning tools have also come to the rescue in this last point. Okay. So the second and third point is what I'm going to talk about today. So before I go on to the first of those two, I guess, are there any questions about things more broadly, string theory, the general setup, what I'm going to be talking about?
And then the question about the complexity of the forward direction.
Yes.
So you say highly complicated math, like how hard?
So depends what you mean. So, okay. So there are, okay, let's say I'm working plugin on box now. Because of the different languages, okay. There's a second instance, okay, which was best of my geometry. I can say, as these integers get bigger, how much harder does my problem become? An ON notation. And what you normally find is double exponential.
Yeah, forward model is double exponential.
Yes. Now, it's worth saying that in my experience, if you're working at kind of moderately sized integers, that's probably a bit of an overestimate. It seems to be kind of okay, but you do still end up finding yourself inverting, well, 10,000 by 10,000 symbolic matrices very quickly. So you really have to limit things quite quickly.
And just picture you have to convert those matrices for forward problems.
Yes.
And ultimately you want to do the
Yes. Exactly. So it is really, yeah, it's very difficult. Any other questions? Okay. So good. So in which case then, I'm going to talk about the first of these. Okay, cool. So I'm now going to talk about, again, on the left-hand side of the thing I had before. How can I,
Going back, so you said the problem is it's very unique.
I think almost certainly not. Almost certainly. But it's not obvious. It also depends what you mean, right? To what level you work at. So there are all these papers that exist in literature of saying they have found a standard model within string theory. But there's often what becomes very important is what do you mean to say you found a standard model? And for example, a lot of people don't count for technical reasons. People often don't count the Higgs as part of the standard model when they do the statistics. What I'm going to do, I'm going to count the Higgs. There will be Higgses in the model I'm talking about. But in principle, a lot of people don't count them. And there's often also a lot of other junk, very large dark sectors, which might cause you problems. So it depends, when you're saying, is it unique, to what level do you want me to answer? You say exactly the standard model spectrum and nothing else? I don't have an answer. If I say the standard model is often defined from someone doing string classification, then almost certainly it's many to one. But again, it's still hard to identify. It's so huge. Right. Okay. So geometrically engineering the standard model for reinforcement learning. And now I realize I've actually done exactly what I said that I shouldn't do in that statement. I should tell you what I mean by the standard model when I'm doing this. For the purposes of what I mean, I kind of do okay. For the purpose of what I mean by the standard model is I'm going to say the minimally supersymmetric standard model where dark sectors are also allowed. Okay. In particular, there's already one whole E8 dark sector, and there'll be a bunch of other moduli that are uncharged under the standard model fields. But it is literally the minimally supersymmetric standard model as quarks and leptons and the Higgs. Okay. So rewinding a second, what geometric data do I need to specify? I need to specify carving manifold. What I'm going to do, I'm going to keep that fixed. Okay. All I'm going to do is I'm going to start playing around with what the other field's doing over my compact space. And in particular, there's one nice construction for bundles over Carving manifolds, these things called mono bundles. Now, the reasons these are very nice, especially for looking at reinforcement learning, or just algorithms as well, is that they are specified by a large number of something called line bundles. Line bundles you can just think of as being a vector of integers. Okay. So as a result, the space of mono bundles over a given manifold is some very, very large integer lattice. Okay. Which is then going to be very nice for the kind of construction I want to talk about. Okay. And just as an example of one of these kind of mono bundles, don't worry too much at the different notation. The main takeaway is that everything here is an integer. This is the only model known, essentially, that was from one of these mono bundles before. Okay, this is the only one that people have found. And it was on this particular manifold, the one we're looking at. So, yeah, it doesn't really matter what it is, but this is this particular manifold. And I specify this vector model V by this whole series of integers. Okay, so this is 3 lots of 1, 0, 3 lots of 0, 1, and an extra 1, 1, and 2, 2. And that, if you compactify the string theory on this bundle, you end up with something that looks like an SO10 gas, which you can then break these Wilson lines to the standard model with the minimally supersymmetric standard model. Okay. But again, this is the only known example for anything that I talk about next. Right. Okay. So, yeah, I'm going to give kind of now just because of the limitation of time, more of a kind of schematic cartoon of what reinforcement learning is. I'm sure there's people in here who know quite a lot about reinforcement learning, people maybe haven't played with it quite so much. But at a cartoon level, what is reinforcement learning? Reinforcement learning is a method of machine learning wherein you have an agent exploring some environment. As it explores this environment, it gains rewards, whether positive or negative, for showing positive or behavior you want to replicate, and negative rewards for things you don't want to do. And typically the way this works is that it's directed by a neural network. Okay, so given where the agent currently is, you give an input to the neural network, a set of observations that the agent can make about the space. So in our case, we have some integer lattice, and it will be telling it, you live at this space in this integer lattice. Okay. Then if it starts, then the action that comes out of this neural network is some probability vector, which tells it what should it do next. Okay. So then follows this policy network, probabilistically exploring the space, gaining rewards and getting punishments as well. And then we use this information of the rewards and punishments to update the neural network very often as it's exploring the space. And you repeat this cycle over and over again. And what you find is, if you've chosen hyperparameter as well, that the rewards gained by the agent will increase over time. Okay. Now, that's a very kind of schematic idea of it, but again, I don't have too much time to go over the full details of it, but that's the basic idea. So how are we going to apply this to our problem at hand? Well, to give a more toy example of this, this also comes from a geometric point of view, but it can be kind of understood very simply. Let's say I wanted to solve this diagram. That is an equation where the variables are integer values. Okay, now it does come from some, or I want to solve this is equal to 18. And so I plotted what that environment looks like over here. The solid dot points are places where that should be repeated. Okay. This is really overkill for reinforcement, I should say. It's going to actually, training the neural network will involve exploring more spaces on here than there are spaces. So it really is overkill. But when I go to the larger environments, that will cross over. Okay, so what am I going to do? My environment then consists of some two-dimensional integer lattice. Okay, and I'm going to place the agent somewhere randomly in space, and the actions available to it are to move to neighboring points in the lattice. It then gains some reward based on this whole quite complicated function. But essentially, the main takeaway from this is that you consider for each point on here, you calculate some intrinsic value to each space on this grid. Okay, so in particular, it's basically saying how close is this thing here to being 18, and that's the kind of intrinsic value of each one with a minus sign. Sorry, absolute value with minus sign. And the reason for that then is that the unique points where this intrinsic value is 0, where it's maximized, are the ones where it's equal to 18. Okay. Then, using this intrinsic value, I can define some reward based on is it moving to, when it makes an action, has it moved to a place that has a higher intrinsic value? Or if it moves somewhere worse, it will get some negative reward. I have to say, yeah, look, staring at this a long time, it may not be obvious this is a necessarily optimal choice. There are lots of choices you can make. This is the one that we found ended up working most kind of broadly for these kind of problems. We have sets of differential equations that happen in string theory. If you want to think, well, I have a reason to why I think this is the case, which is if you stare at this for long enough, when P is 1, this is a telescopic sum. So really what you're maximizing in reinforcement learning is the sum over all rewards in an entire episode, and all the intermediate ones that can cancel out in this case. You're just saying that given I run an entire episode, I start somewhere, what is the relative difference between there and the final point we end up at? That's my intuition to why I think this works. Okay, anyway, so I have that, and there's a bunch of other things I can do. For example, include a terminal bonus for finding this terminal state. Okay, so now I go ahead and train my neural network from the agent exploring this space, and what do I find happens? So, okay, so this is what ends up happening. In particular, the loss starts going to 0, and after a couple thousand rounds exploring, again, so it really equals over the agent will explore, will visit more than there is states in the space. You find that the agent is, on 100% of the time, is finding one of these terminal states. Okay? So if I now place the agent somewhere at random in the space, it will wander to a nearby terminal state. Okay? And now I've got my trained neural network. In principle, if I had a larger environment, I can start placing him at random places all over the space, and allowing him to slowly build up a database of all the terminal states I have in the space. And so this kind of image here is what you should be kind of thinking of how the neural network could use the final space, which is that each of the terminal states will have some basin of attraction. Okay. And if the agent was to be initialized somewhere in that basin of attraction, then it will wander over to that terminal state. Okay, so this is the basis of how I'm going to be solving all of these kind of problems from, well, I'll bring up one example of how we solve multiple kind of sets of differential equations that come out of string classifications.
Can I just a nice question about how to think about this? So, is the vector of integers that's associated with one of your line bundles supposed to have some notion of locality in the sense that changing one of the integers by 1 leads to a compactification with like similar physical properties, so that the agent is kind of looking at nearby and doing small changes, or is it not?
I don't think there can be small changes. So actually, in the full case, I really don't think they are small changes. Now, okay, you're right. There's sets of differential equations, so they are smooth in some sense. But actually, the physical properties that we're talking about, I do the cohomology calculations, are very much not smooth, where it basically comes down to these integers end up referring to degrees of different polynomials in these cohomology calculations. So I don't think the locality point is actually that important.
So the agent is not using some sort of local sniffing out of what makes it better. He's just trying to go through a lot of bad states to get to it.
Exactly. Now I think that, yeah, and that's why I think the telescopic sum is important, right? The fact that the intermediate steps cancel out. Because if you can imagine that I started the agent somewhere and its nearest terminal state was the other side of some big hill, then in principle, if I was including all the negatives, I'd get some huge negative rewards that try to get up the hill and come back down the other way. But what I'll probably try and do is might try and go around this hill in some way, or go off to a different terminal state together. I think with this telescopic sum, it doesn't care that hill is there, right? In terms of it just knows, all right, if I'm going to once I'm trained, I can just ignore this. I just have to get to the terminal state at the end. Now, there's of course edge effects to this. I have to limit the size of the episode, but I think this is an edge effect over the full training in that way.
Thank you.
Right. So, okay, given that, now how am I going to map my mono bundles into being, well, how can I make it that I can describe this in a way that reinforcement learning can understand? So, well, as I told you before, really, monobundles are described by just a large number of integers. Okay. So what I'm going to do is I'm going to consider this as being some large integer lattice. Now, it does have some small constraints in this as well. I'll come to in a moment, because actions, well, naively you think that the best action is, okay, I'm just going to move the neighboring points in this lattice. There's a slight trick you can do, which is that because you have this condition on your integers, actually the more natural action is you kind of move more diagonally in the lattice. You move two of them by one. And the reason for it is that you can keep this condition fixed. You start from that locus, where that condition is true, and then you remain in that locus forever. So you just inbuild, rather than forcing more things onto the reward function, you can keep some of it in the nature of the environment. Okay, so now, what I'm now going to do is I'm going to define some intrinsic state value, again, for each state in my environment, and use exactly the same kind of setup for the rewards like I had in the toy example in the previous page. Okay, so this intrinsic state value, I want to introduce it in the next slide. It's a little bit scary, but don't worry about it. I can just kind of say the main takeaway from it is it is a measure of how close you are to being the minimally supersymmetric standard model. Okay, and some of these things are mathematical requirements, some of them are string theory requirements, and some like the equations of motion of string theory, and other ones are phenomenological requirements of right numbers of quarks and leptons. Okay, so these are all the parts that go into it. And so as I was saying, yeah, that there's multiple things there. So for example, the in a sense, the equivariance and an index match condition, these are a level of, do I have three families of quarks and leptons? And also, I was saying this Wilson line situation, can I actually break this to the standard model? That's kind of what the equivariance condition is testing. Can I introduce an appropriate Wilson line over the space? Other conditions on here, the anomaly condition and the stability conditions. These are essentially saying that do these actually satisfy the equations of motion of string theory, or am I just constructing an arbitrary bundle over an arbitrary manifold that doesn't actually have any meaning to string theory? It just happens to be. I mean, as a mathematical object, it's perfectly fine, but it's not. Wouldn't solve the equations of motion. And then the other ones also exist in here. These are kind of more mathematical. So the trivial bundle condition, split bundle condition, the bundle condition. This is just mathematics in some sense. That the space of monad bundles, as I introduce them, describes actually something more general than bundles. And this is making sure I haven't gone to this more general construction of some kind of sheath, and I am actually looking at that. Okay, so all these things go into this. Okay, so given this, exploring the same space as the known model and limiting the size of the environment to some size, I think there's 10 to 13 states in this thing in total. 10 to 13 candidate monad bundles. So 10 to 13 states in total. After only an hour, just on your laptop, just a single CPU, what you'll start finding is that the terminal fraction, so how many at the end of the terminal state, essentially goes to 100%. Okay, so you're left with this agent that, if it explores this environment for, I didn't actually write it down, I think it's 32 steps, it will find a terminal state within 32 steps, so almost 100% of the time. Okay, and then again, within this hour, after doing a few extra checks that are going to take too long to do during the training, we end up finding there's 15 models in the space. So just again, give a comparison there that over the kind of the 40 odd years that people have been doing geometric string verification, they're able to come up with one example of constructions in this way, and just by putting it with a reinforcement learning algorithm for an hour, they found 15. So it really is, yeah, the speed in which these things work is really quite incredible. But once I have this trained agent, I can now, this part first. Something that's quite nice with reinforcement learning is I can try and work out what is the actual neural network doing. Okay, so I can then go and I can plot all the different conditions and see which one is it solving first. And it turns out what it's doing is it's kind of doing, maybe in some sense, what you would might expect it to do, which is it is solving the inequalities first. So I gave all these lists of conditions. Some of them were equalities, other ones were inequalities. And what the neural network seems to be doing is moving in general to some region where a lot of these things are satisfied, and then fine-tuning down afterwards, okay, to satisfy the equalities. Okay, so now I've got this trained neural network, I can now keep repeating, starting at random points in my space, and just building up a nice little database of monobundles. And if I do this, what I then find is that eventually the number of new states I'm finding, so the fact this is larger, don't worry too much about this. This is because this is from the extra constraints I pose after the training. What you then start finding though is this then starts to saturate, which then becomes kind of indicative that there's probably not very much defined in the space afterwards. And in particular, we end up with 35 models again, where there was only one number before. And just as an extension, which I didn't include here, it's the space to another type of covariant problem. Then you find order 500 in there when none were found beforehand as well. And just kind of as another comparison of similar kind of methods, we also tried using genetic algorithms for the problem. And in this case, it found a similar success. But again, with detail, I don't have time to go over the complete details of it. But the thing that's quite nice is that since it found almost exactly the same number of states as this one. So with two very different methods, you end up finding basically the same set. That's kind of indicative that there probably isn't anything else in the space, or if there is anything, there's very, very few other things. Okay. But again, just one more quick comment on genetic algorithms of discrete optimization. In another case, we were looking at, to give an idea of how efficient these algorithms might be for the kind of problems you have in string theory. We took an example where there are a lot of tricks you can do. Okay, so this is a different type of string construction called sums of line bundles. Again, exactly does don't matter. The thing that's really nice is that there are, even though these are huge environments, there's a lot of mathematical tricks you can do. To really slim down the number of things you have to scan, you can then go and do an exhaustive scan and find all of the models in the given box. Okay, and just then, okay, so this is the comparison with genetic algorithms or reinforcement learning, we did try both, compared to the scan. You then find that, okay, I mean, in these cases, that volume squaring 10 to minus 10 over the space, you still found the whole thing. The one I find most incredible though are these ones, that even though it didn't find everything, you've only explored 10 to the minus 19 of the total space. So that really is an incredible speed up from these methods for discrete optimization. Okay. So I now want to talk about the second half of this, which is again solving PDEs for string applications. But are there any more comments or questions about discrete optimization and model building? Yeah.
Is there any sense in which you're not really trying to find a greater solution? Maybe this makes me enough.
Depends what we want to do. So I mean, in terms of if you want to then start, and there's people who want to try and get string applications that have every detail of the same model, and having as many early candidates as possible is obviously a good idea. I'm not sure if I'm necessarily personally interested in getting that exact goal. So I decided that's what I think those people will be very satisfied if they found almost all of them. And then they can have other things. So just one example of this.
Just kind of compare the you compare it to genetic algorithms.
Yes.
But if I did just some kind of reading walk.
Zero.
But
Zero. You find that.
And then within each trajectory, how many steps are you taking?
For the so for the reinforcement, I think in both cases it was 32 steps.
So I have 32 steps to move in this integral lattice.
Yeah.
But you
But it's very high dimensional.
But when you say the number of states you're visiting, you're counting the ones that are being touched along the way.
Yes, exactly. Yeah, so that's what I mean. Basically, yeah. So when I say this kind of thing, for example, this is we describe it now. How many computations do I actually have to do? The expensive computations I don't want to do, how many of them do I have to do? And the answer is 10 to the minus 19 times less.
Right, and for 32 steps, oh, yeah, that's telling you, if I divide by that, that's the number of trajectories.
Exactly, yeah. Right. Okay. So yeah, there's no other questions about discrete optimization. I'm going to go on to solving PDEs for string applications. So as I was saying right at the start, that if you want to try and get kind of finer detail about your the field theories that come out of string applications, you need a lot more detail than just the topology. You actually need, you can't just say, there in principle exists a solution. You do actually need to go and find that solution. I'll give some details of why that's the case in a moment. So you actually need to get this geometric data. And so one of the things it involves you doing is actually finding the metric of over this covariant. What is actually G mean U equals what? And yeah, despite the fact they've been studied for 40 odd years, there are no known analytic expressions and metrics on Clavier 3 folds. I always find it kind of amazing that string theory is developed as far as it has at all, considering that's the case. But it's, yeah, just but Yeah, but now using these methods to solve PDEs, we can actually go and solve this. And this is essentially equivalent to solving six-dimensional Einstein equations coupled to matter. Now, given with the assumption of supersymmetry to make some of the equations. Okay. And so yeah, so we managed to do this in one particular type of string application, in particular the line number size. What we're going to do is we're going to have a set of differential equations with the solutions are represented by neural networks. Okay. And again, just really emphasize this is the first kind of calculator of its kind. It's really made possible by machine learning. This is the paper that came out earlier this year. So, why do I actually use geometry now? So let's say I'm doing some string application. What does my 4D theory look like when it comes out the end of this? Okay, so I'm going to have some set of, this is basically four-dimensional supergravity geometry. There's a few different features in here. So I have my holomorphic Yukawa, and there's some integral over the triangular function with three of these news. So I'll tell you what the news are. We have some object, we have one of them for each field. Each matrix field in the 4D theory. Okay, and this in principle you could go and calculate this. I mean, realistically, you still need to do the integral numerically, but you could go and do this. This one, however, this field space metric, those of you who know some different geometry might recognize the star as being the Hodge star. And so this brings an explicit dependence on the metric. So you can't actually compute the normalization of your fields without having the metric on the platform. So the actual meaning of these holomorphic Yukawa elements is essentially entirely meaningless without having the normalization of the fields as well. Okay, so what are these news? Well, okay, I have these two equations, I have news in them. I'm just going to tell you where they come from. So if I have just an example, scalar in some 10-dimensional theory, okay, then it satisfies some Cosman equation. So this thing, I should already say equal to 0, where inside this rows. This thing equal to 0. If I'm now going to compactify this down, my Laplacian splits up into a 6-dimensional class and a 4-dimensional class. Okay. I'm now going to use separation of variables and expand my field in a basis of functions on that compact space. And this is what the news are you had in the previous slide. Okay. So these bases of functions I'm choosing are ones that are eigenvalues of the Laplacian, such that I now have an infinite tower of scalar fields in 4D effective theory, each with a different mass corresponding to the eigenvalues of the Laplacian. Now these heavy ones are all they're all super heavy. They're order compactification scale masses. They're really, really giant from string theory point of view. So really all we're ever interested in is the zero modes of this. Okay. And in particular, the reason I could calculate the I could tell you what the low energy spectrum was, the massive spectrum was, because it turns out the number of zero modes of the Laplacian is a topological property. Just counting the number of zero modes you can do without having to solve the equation explicitly using these topological arguments, and in particular cohomology. Now, how does this generalize to our particular case? Like, okay, this is all well and good that it works for a scalar. And what we really need to do is we need to find zero modes of this now, where the derivative is a covariant derivative, where the gravity covariant derivative and a gauge covariant derivative. Okay. And again, you can count the number of zero modes using cohomology. But now I actually want to go and calculate this news because they're clearing this equation I have above, as well as the metric. So what I need to go and do, from the geometry point of view, is I need to go solve Einstein's field equation, 60, to find the metric. Once I've got the metric, I can then go and solve Yang-Mills in 6 dimensions to find the gauge field. And then I can then go and solve these kind of equations to go find the actual representatives of these zero forms, these zero modes of different derivative operators over the compact space. Okay, and in each case, I'm going to represent all of these by a neural network. So this is the string model I'm working with. This exists in a different manifold this time. This manifold is some subspace of 4 projective spaces. If you're not familiar with, then there's some polynomial vanishing in this space. If you're not familiar with projective spaces, don't worry. You can think of the space being 4 different 4 spheres. Okay, and then I have one complex equation on 4 ones, 2 real equations on the 4 spheres. So my 8-dimensional ambient space becomes a 6-dimensional space, and it turns out that the degree that this polynomial is in, that 6-dimensional space is a quadratic manifold. Okay, and this is a set of integers again, which basically specify my what the vector bundle is doing over the quadratic manifold. And yeah, and there's a few other things as well. So this is then a standard model. This is a stringy standard model in that I have 3 families of quarks and leptons. I also have my Higgs's. And although this kind of fits into an SU5 like structure, there is no actual kind of gut regime of this because this will break, but it kind of has a SU5 gut type structure. Now, the kind of caveat I have to come with this is really a proof of concept calculation. We're not expecting going into this that we're going to get any kind of realistic matters. It's more that this is the first time anyone's been able to do this kind of calculation at all. In particular, just the level of flavor symmetries will exist in this particular field that comes out of it. What you'll find is that the down Yukawas, they will vanish. And up Yukawas has this very particular structure, which in particular means that one of the masses for an up type, the up quark is massless in this particular model. Not only all the down type one's massless, but the up quark is massless. But again, this is the first time you can really ever calculate this. Actually, one thing worth noting is that this also serves as a nice check. We don't put the down Yukawas and the up Yukawas. This actually serves as a nice check on the methodology, because you can confirm, you can still go and try to keep these zero. And you just find they actually do come out as like numerically zero. So it's a nice check that the method is does actually work. But that the method respects up to numerical error the flavors that you expect. Okay. So what are all the different things I'm going to try and solve? So the first thing I want to do is I want to try and solve for the quasi-realistic. Okay. And the way we go about this is we first of all have, sorry, the same for all of these cases. So I have to find parametric, the gauge field, and these one forms. And in all cases, the way we do it is the same. But we have some reference quantity, whether it be this GFS, HFS, or UREF, which is in some sense in the right kind of topological class. Okay, which we can then find by hand analyzing it. What we're then doing is we're shifting in this topological class to find the correction to actually get the real metric we're interested in, the real gauge field we're interested in, and the real one form we're interested in. Now, when I say a correction, this is not correction in the sense of perturbation theory. There is no expectation these shifts are small, but it kind of fixes the topology of what's going on. You're just moving within a particular. Okay, anyone who knows again a bit more mathematics, you're shifting around within a given homology class of some type. Okay. Crucially as well, though, as is often the case with kind of geometric data, things have to transform in very particular ways. Okay. So this the shift I have the gauge field is theta, and the shift I have the metric is phi. These have to shift as functions over my quadrant plot. And as well, this sigma here has to transform the section and we get line model over my quadrant plot. So one thing that we found very helpful was, of course, looking at equivariant neural networks to try and realize this. So going from, okay, again, people who may know a bit more mathematics, please forgive me when I say tensor or something that transforms like a tensor, but that's basically the kind of idea I want you to take away from this, is that, say we're just working on one projective space. What does this look like? This essentially looks like I take two-dimensional complex space, I remove the 0 points, and I then quotient by an overall scale. Okay? So what does that mean? It means that I specify a point in projective space by 2 coordinates that are identified to any scaling by a non-zero complex. So you consider these two things to always be the same thing. So if I'm defining a function over my projective space, then what do I need to do? I need to make sure that they are invariant under that exact kind of rescaling. Okay, to be a well-defined function in the projective space. And so the way we realize this is in the following way. We make it that the input, the first layer of the neural network, is invariant under that exact scale. So the way we do that is as follows: is that for each coordinate, you then multiply it by the conjugate coordinate. So if I have just x and y, the single p1, I have xy bar, xx bar, and yy bar. That has all the information I need to construct all the points on p1. And that because one is barred and one is unbarred, that cancels out the overall phase, because they both rotate in opposite directions. And then to get rid of the magnitude, I divide by this x squared plus y squared. And that's basically the only thing you can divide by for projective geometry, because the only time this vanishes is the 0, which I've removed from the space. Okay. Now, very analogously, I can do the same thing for sections, where again I make the input. So sections are different. They can transform in different ways depending on what line model they come from. But in principle, I specify n, they have transform as lambda to n under the scale. Okay? And so this is exactly the same way. But the first layer of my neural network, I make invariant. When I go through the whole neural network, it has to remain invariant all the way through. And what I then do is I then dot the output of the neural network into a set of things that do transform in the correct way. So in this case, the monomial is x squared, x and y squared. So as a result, if this was a lambda with integer 2, this is now going to transform in the correct way. Okay. And this guarantees these are good functions in good sections over a single projector space. And there's natural generalizations of this. Objects through products of projector space as well. Right. So given that, that fixes one of the conditions I have. Well, I still need to go and solve the field equations and everything else over my complex space. So it's just an example of some levels just loss goes down, but I'll see a bit more sophisticated in a moment. This is solving for the quasi-metric, so loss going down. This one is a bit strange. I'll come back to in one moment. So these are both solving for different gauge fields over the quasi-metric. And the last one is then solving for one of the example news, one of the example one points over the quasi-metric. So what's going on up here? This one doesn't look so good. So why is this happening? And this is another nice check that this method actually makes sense and works, because I was mentioning that in order to solve the equations of motion of string theory, there are topological conditions that get imposed on the underlying bundle. And what I have here is I have one that actually appears in my model, which satisfies those topological conditions. And the one up here does not satisfy those topological conditions. So on mathematical ground, you do not expect this one to have a solution. There is no solution to this equation, mathematically, provably so. And as a result, you then find this happens. So while the training loss does start to go down, the validation loss, well, okay, is very messy, but it does start to go down. Validation loss also remains very high. Well, in case you know there is a solution, you find this kind of characteristic. Okay. So taking all those pieces, putting them all together, we can go and actually calculate some quark masses. And what do we find? We find that, okay, so the choice of what I choose a one parameter bound in moduli space, and I'm plotting that along here. And I have three different curves here. Let's go through the order. The first one is, if you were naive and you said, I can't calculate this field normalization, I can just calculate the holomorphic couplings. This is what you expect. And to be honest, when people have done kind of flavor physics and string theory, this is almost always what they've done. It's a very naive step. However, if we then instead use the one from the numerical metrics, which is the orange curve, you find it's quite a lot larger. One thing that's quite unexpected, and I think was a surprise to all of us, is let's say I just chose these reference quantities. Okay, so these are the quantities that were in the right topological class, but had no expectation to solve the previous motion. Kind of unexpectedly, these are actually all, if you plot that curve, it turns out to be within about 10% of the actual values, which is kind of interesting, and it gives you a tool to, if it's true, maybe provably true that they should be close in some way, then that gives you a way of maybe exploring larger parameter spaces for these kind of objects first, and then doing an expensive calculation to train the neural networks at given points in moduli space. Okay, and just also some other points to make notes here. In particular, just statistically, running these things over and over again, we find there's about 1% error.
Exactly.
So okay, I was a bit quick here. So the x-axis is, sorry, let me go back a bit. So I specified that this is some hypersurface in direct spaces. And in any string application, you have a bunch of moduli. I fix the topology of my space, and there is, but the geometry of it is unfixed. Okay. In particular, some of that geometry comes down to the parameters of this defined polynomial. Okay. So what I'm doing here is, I forget what do you remember what we set psi 0 to? It was 1. 1. Okay. So what we did here is we set psi 0 to 1, and I'm exploring a range of psi, just to get an idea of how things change. I think you can see that here. Sorry, it's very small. You're saying this is how things change with psi units. Okay. So it's how things change with some geometry of the complex space. Okay. So, yeah. So I'm nearing the end of my hour. So I'll just conclude there and just say that methods from data science allow searches for interesting string vacua, in particular those ones you can engineer the MSSM or maybe other or other field theories that have interesting properties in other ways. using reinforcement learning or also genetic algorithms. And secondly, we've been able to solve Einstein's equations and Yang-Mills equations in 6 dimensions by using these machine learning methods for PDs. And just kind of, the kind of 2 takeaways is that the first one, I want to emphasize that these methods are not really specifically for string theory, the first one in particular, and that there are other large landscapes of physics that are discrete in physics, and maybe the same kind of tools could be applied there. And secondly, as well, to emphasize that really this was the first time we can be able to calculate these kind of quantities from a string application. So yeah, a little bit better. Any questions?
I know this out of curiosity, you say solve Einstein's equations at 16. So is the main obstruction the 6D-ness, or is it just the fact that you're solving on weird manifolds? Like, if you want to solve on weird 4D manifolds, that'd be easier.
Well, I'm not a numerical relativist person, but I think solving Einstein's equations in general is hard. I mean, the only reason I think we can push to 60 at all is that we have to do something. Now, okay, there is an expectation for what this metric should look like as well, just intuitively from looking at lower dimensions. And in this case, do you know the Weierstrass B function? You heard of it? Okay, so it should look like a higher dimensional analog of the inverse Weierstrass B function. So anyone who doesn't know what that is, just know it's probably pretty horrible. And then somehow this thing ends up being smooth at the end of the day. The second thing as well, which also maybe is of interest, is that I said that there's this theorem by Yao. It says given topological conditions, there is a unique metric. That theorem, that proof is non-constructive. It just tells you it's there. It doesn't tell you where to actually go, how to go and find that metric or how to construct it. So those 2 things, I guess, apply. Does that answer your question?
Yeah, I guess I'm wondering if you have like LIGO scale resources and you throw like a massive numerical relativity code at it,
Yeah.
you just do it, or
I mean, more compute will probably always help, yeah, but I'm not watching.
What's the so singularities? I mean, so singularities care about formation singularities. We don't have to worry about that.
That's true.
We know that the manifold's smooth. It will get a lot more complicated.
Yeah.
If you're expecting, also if you're trying to make more than that.
That's a good point, yeah. So the fact that also we're in Euclidean signature, we don't have to worry about things like horizon development and stuff that numerical relativity. There are other reasons why this is so sense.
So coming back to the first part of the talk, so I usually think about the MSSM as being not particularly special. It's just some set of particles of field content, and it doesn't seem to be, it doesn't seem to have any structure that would help you, for example, find it.
Yeah.
But now you're telling me that you can find examples after exploring a tiny fraction.
Yeah, tiny
of the landscape. Do you expect that holds for more general criteria that you might be trying to solve for, or is there something special in the specifications of the MSSM that actually is allowing you to get
that is that's
a bit better? Like, and maybe another way of asking my question is that when I've heard people talk about string phenomenology, the target is always MSSM-like theories.
Yeah, no,
but you could target completely different types of geometry.
Yeah.
Would it be just as easy or harder? Would you have any intuition?
That's a really good question. Okay, when you're asking to what level are you saying MSSM? When you say the MSSM, to what level are you defining it? Because again, it depends a little bit on what you mean there. Yeah.
Right. So maybe I have a giant space. I have a fraction of that space that I think satisfies some criteria. How much of that space do I have to explore? Of total space do I have to define that? Okay. And so I can define MSSM super narrowly, I can define it more broadly, but there's some sense kind of a ratio of how much of the space I have to explore.
Yeah.
And
So
have you just drawn a giant bullseye that makes it really
in this case, yeah, I don't think that's the case. I think, yeah, I mean, I suspect if I chose any field theory, it's probably going to be, but that's my suspicion.
or equally easy?
Oh, well, there's a dependent point of view. Yeah, that's true. Or equally easily. Well, okay, maybe not. In terms of the nature of the construction leads you into very particular types of field theories. In particular, the whole setup I have for the monobundles. You are trying to head towards something that is at least kind of gut-like in some sense. Now, I could have imagined doing a completely different construction where you end up with some wild, different low-energy gauge group. In which case, obviously, never going to find the answer. But maybe if you then specify some field theory within that, then you find it be just as good.
I found this thing about the closeness of the quark masses between your reference topological metric and the final one being very surprising. So I have a vague question, which is I can imagine two reasons why that's true. One could be that for some reason, the choice of metric in the topological class that you picked happens to be luckily very close to the correct one, or a different reason could be it is not very close to the correct one, but somehow the direction in metric space you're moving in to get to the correct one somehow does not affect the quark masses very much. So do you know which of these it is?
I suspect it's the second. But this is just vibe space. I don't really have a very good reason for that. The best reason I can say is that I would have, okay, one of the possibilities that you think of is maybe that we did limit ourselves to begin with to this very limited area in complex structure space, a complex structure moduli. We just decide so much. Now, if the first of your ones was true, I would have expected the first thing you check is go to somewhere far more generic in complex structure. And then see, does it still hold? And the answer is it does still hold. So unless there's something very particular about this exact bundle and this exact manifold, which I find very weird, very surprising. I don't think it would be true. I think it's probably the second.
I see. So if you did some other check of closeness of the two metrics, because essentially, I mean, you have two different metrics, and you could sample random points on the manifold and random points of pairs of tangent vectors and just difference the ds codes. Right?
Yes, that's true. Now the problem is, of course, we're just talking about numbers, where the number of models we've done this for is currently 1.5, I guess. So I don't really have many big numbers to go on because they are expensive calculations. But I suspect the second option. But I don't really have.
There's also this point that there's a different approximations to try and get these metrics, and in some sense, the zero order approximation is what we start with.
Okay, okay. I'm not talking about localization calculation.
No, I'm not talking
Okay.
about the P operator ones. The zero order, you start with the embedding.
Okay, so there are traditional algorithms rather than machine learning.
But there's no expectation that that zero order approximation actually is any kind of approximation.
Yeah.
So it's sort of interesting that end up being it. But there is a way in which you can talk about the reference approximation we make as an actual approximation, but it's totally uncontrolled. Like we have no idea how much it's interesting it actually ends up being.
This is the statement that the reference is not actually a solution to anything.
Right.
Yeah.
No, but he means something slightly different. He means that there were these traditional algorithms by Donaldson, which basically consists of you having a given ansatz for the metric in some sense. And then you can then try and find numerical approximations within this ansatz. And if you kind of do the 0th step of this algorithm, what you have is the reference quantity we wrote down here.
Okay.
Now, the fact I do the 0th order something and something that only converges and then goes to infinity, the fact that's not anything close to it is still kind of surprising.
Yes. I see.
Is there a question online?
Hey, Thomas, it's Jim. How's it going?
Yeah, things are good.
Good. Sorry to not be there in person. An easy question and a more speculative question. Just to make sure I understand, your Yukawa couplings that you showed, obviously you're computing the physical ones, but were the texture zeros coming from the holomorphic part, or were they coming from the normalization?
The holomorphic part in this case, but there is also a texture to, so there are flavor symmetries that mean that, yes, basically. Okay, so if I come to this, you look at the U's, right, as well. So the non-zero ones, only these two rotate into each other as well.
Mm-hmm.
But you only have to worry about the normalization. Except for the actual mixing, we have to worry about the rotation of those two into each other and the overall normalization.
Okay, good. But so it is this sort of story that there's texture zeros in the holomorphic part that are then getting mixed in and normalized via the normalization from the kinetic terms. Okay, thanks. I just wanted to make sure I understood the claim. The other thing was, of course, I know how hard these calculations are. Most people think that the landscape lives at large numbers of moduli. What are the prospects for scaling up to complicated cases?
So it depends what you mean. So it's not okay. I suspect the biggest obstruction we have is H11. Now this might be slightly naive, because the reason I suspect that it might be slightly naive is that we're working with sissies. And so the codimension also increases with H11. So I don't know really if the obstruction is codimension of how we constructed the manifolds, or if it's H11. But I also think that's kind of thing. H12 I don't think is really much of an obstruction. H11 is potentially an obstruction.
Because I mean, I guess there's two questions. There's the questions about the metric in the first place, then there's all the extra stuff you need to do to get the standard model. Because the techniques have already been extended to up to 491 in principle, right? In Kreutzer-Skarka, but because you're doing CCs, you're saying there's limitations coming from the way you're actually doing the heterotic constructions. Okay. Okay. I see, but okay, thanks. But you're not in.
I mean, the numerical, ignoring the standard model side of things, just the numerical metrics, I suspect they might go badly with H11. But again, that might be, it's hard to know if that's because of co-dimension or because of H11. And we haven't really explored applying these to Kreutzer-Skarka.
I mean, I guess it probably makes sense to work on scaling up the numerical metrics as much as possible because you don't have to do all this extra stuff. As a start, okay. Yeah. But have you guys tried to do that? I mean, how far have you gone?
With H11, this manifold probably. I don't think we've got anything like
Okay. No, that's good.
Yeah. I mean, on CCs, this is
So,
yeah.
No, I was going to say, on CC, this is the highest we've gone. Now, in principle, the CY metric package does do Kreutzer-Skarka, toroid geometry. I haven't explored that, so I don't know if you have. Well, Fabian's probably the one to ask, actually.
Okay. Excellent. Thanks.
All
Great
right,
talk.
Here again. Everyone, grab stack on your way out. Otherwise, I think we'll be continuing up at the penthouse. Yes, exactly. Great. All right.